The following content has been provided by RWTH Aachen University.
So this is now when you are on top of the button, and not well, if I'm away and I have to reach and touch the button, and that is done in Fitts law. Yeah, as I said, so with the CMN model, we can estimate, well, how long does a person take to react to something and press a button or whatever. Now is the question, well, how does it long to reach a button or a target for that? And for this, we have experiment number 4. So on the other side of the sheet, you have a set of lines. And so, for example, if we have 2, I will give you 10 seconds and would ask you to tap between these lines as fast as possible. So reach from one to the other for 10 seconds. And try to tap inside of this, but it's no problem if you miss it, just continue on. But try to reach it and try to do it as fast as possible. And I will tell you then the 10 seconds. So for the first two set of lines, just start 3, 2, 1, go. And stop. Yeah, I should have said don't use your best pen or your mother's heirloom for this, because, well, you might go too eager a little bit. So now for 0.5 centimeters and 8 centimeters distance, so the second one on the sheet. And stop. And stop. And stop. Has some meditating quality for me up here, just listening to that. So, widest targets for 4 centimeters. 3, 2, 1, go. And stop. And stop. So, yeah, that was the sport for today. Now, what I want you to do is to just focus on the left side that you're having there and count the number of dots that you have inside. So, yes, it is tricky. If you're missed by a little bit, count that as well. But if you're somewhere here, don't count that one. But just now here on the left. And do this for the whole side there. Now I need to have a couple of numbers again. So third row from the right, for the half centimeter width and 4 centimeter distance, how many taps did you have? 12. Same sheet. Yes. What did you have? Yeah. 14. That is 14. 14. 10. 9. 11, 30, 30 or 13? 13. 30 would be quite impressive. Yes. 14? 7. Okay. Then let's go to the 8 centimeter width in the next row. 10? 11? 16? Also 16? 10, 8, 7, 9. Is there someone else in that row? Were you asleep? 10. Random number, or did you have that? And now for the, well, 16 in the next row? 10? 7? 11? 11? 10? 6? 12? 8? 15? 8. Okay. Interesting, the numbers in the people sitting in each row grow up. So, do I continue there? If we look at the median there, if we take a look at the numbers here, so the mean taps per task, what is something that you see? And also, when you look at your own sheet, what happens when I'm increasing the distance? Yes.
I don't know. I get the same results for all.
Oh, interesting. Okay, someone else. No, in general, what can you observe when you increase the distance but keep the width the same? Yes.
You can do less dots because you have to go further.
Further. All right. What happens if you increase the width? We don't have that one here because I was too lazy to record it.
More points.
More points, so it gets easier. So when we would like to have a formula to calculate the time I need to get to a certain position, what it appears like that the distance, if I increase the distance, that it has a positive relationship there. So if I increase the distance, I take longer to get there. While at the same time, as we've seen with the width, if I'm increasing the size of the target that I want to hit, I'm taking less time. So we expect something to be like this. So now, if you look at your numbers, well, let me just get back here. If you take the same width, but double the distance, so between the 4 centimeter, 8 centimeter, 16 centimeter, what happens to the numbers? Do they double as well?
No, they just decrease a little bit. I think most time you need to aim for your target.
Okay. So yeah, is that what everyone has seen? So if you increase the distance, it doesn't take you twice as long to do this than to do that. So it's more, yeah, it's less than linear. What would be a nice non-linear function there?
Explain that.
Logarithmic. Yes. So when would say, well, if I double the distance, I'm more adding a constant to my amounts of tap that I'm having. So expect, where do I have it? Something along the lines here of a log function there. And also, what's interesting is, or if you take a look at when you double both conditions here, so compare how many taps you have for the 0.5 centimeters, 4 centimeter distance to the 1 centimeter and 8 centimeter distance, and 2 centimeters, 16 centimeter distance. What do you recognize there, or what do you notice there?
For me, the numbers are approximately the same.
Okay.
17, 16, and 18.
All right. What happens if you look at, what's the other one that we're having? 1 centimeter distance, 8 centimeter difference, and 2 centimeter width and 16 centimeter difference? That was the same in there, right? No, that makes no sense. 0.5 centimeter and 8 centimeter and 1 centimeter and 16 centimeter. Is that true there as well? That they're also very similar? Which would point that this is sort of true, so that these cancel each other out or have an effect on each other. If I'm doubling the width, and doubling the distance, well, the number of taps that I'm having is tends to stay similar. And so this is the data that we got, I think, 2011 or something, where we actually recorded for everyone the number of taps that they are having, or they got. And yeah, it showed there as well, if I'm doubling the distance, it's roughly a constant to the execution time that I'm having, so which indicates that it's a logarithmic relationship. And that doubling the target gives about the same results as halving the distance, which we also saw when I'm doubling both. I'm getting sort of this similar number of taps, which we can, for example, see here. If I have the 8 centimeter distance for 0.5, I have roughly the same. It takes me the same time as if I have 1 centimeter target for 16 centimeter distance between. Now here's the seconds that I'm taking to reach the target. And this is basically what Paul Fitts described in his law. So which is a target where, or a task where I'm switching between 2 targets and trying to hit the target there. And he wanted to calculate or to optimize a jet cockpit. So he was working for the military, and well, in a jet fighter, there tend to be situations where you want to reach something fast, like, oh my God, I'm burning, I want to eject. And if there's a small button somewhere that I have to flick up, that might not be the best one. And he tried to see, well, how can I optimize this, and how can I calculate or get an estimate how good the cockpit is. So yes, that is he did it well in a jet cockpit, but it also was adopted for display systems, so or in various input systems with a mouse. Just the regular tapping is the original one, and basically this is one of the most robust models that I've come across. So whenever someone is developing a new input system, this is the system or the model they're using to compare how it fares against existing systems. And yeah, the formula he developed is reliant on the distance I have to reach the target and how big is the target. And the results is Fitts' law, which he also published in the middle of the 50s, where I have the result, the time I need to get to a certain position. It depends on a index of movement, which is here arbitrarily set to 100 milliseconds for rough estimates. That was proven to work fine. And it's measured in milliseconds per bits, which makes sense when I show this one. And the second parameter is the index of difficulty. So how difficult is it to reach this target? And this is dependent on the distance and the width. So sort of similar to what we already observed in our in this little experiment. And since it's a logarithm to the base of 2, you can say, well, this is in bits, and so when you combine these, you get a time in milliseconds that you estimate well what it takes to reach this target. And this law actually can be derived from the CMN model. So what we've shown before. So how long does it take to process something? And we're not showing this here, but if you're interested, just come to me afterwards or whenever and ask me. Don't ask me. No, you can ask me. So this is actual data that Fitts found out. And here on the y-axis we have the time to get to reach a target in seconds. And here on the x-axis we have the index of difficulty, which is a logarithmic scale. So what he observed was, well, he can roughly place a line in there with the slopes of the index of movement, which is the 100 milliseconds per bit. And you can also see, well, it doesn't precisely hit it here, but it was good enough for so that he could estimate the time that it would need the pilot to reach a certain button. Yeah, depending on the width and the distance.
This content was provided by RWTH Aachen University.